Hello and welcome to this recap of chapters 17, 18 and 19. We're going to be looking at the bipolar junction transistor, otherwise known as just a transistor. We're going to be looking at how a transistor can be used to make amplifiers and the different class of amplifiers and their efficiencies and uses. And then finally we're going to have a look at something called an oscillator and the three different types of oscillator that you need to be aware of for the exam. So what is a transistor? Basically, it's two diodes end on end, where you have either PNP type or NPN type, whereas NPN is the far more common type. And they can be used as electronic switches or amplifiers. A good analogy of a transistor is a tap, where you have a collector, base and emitter. The collector collects the electricity, or the electrical current, conventional current. The emitter emits the conventional current, and the base controls the flow of the current from the collector to the emitter. Now, that's done basically with the amount of current on the base is magnified by a certain value called the beta value. Before you can even get a transistor to function, it has to have a initial 0.6 volts on the base, and that must be higher than the emitter. Now this is a very common question for the exam, that the voltage on the base must be over 0.6 volts just to get the transistor effectively to start to allow current to go through it. Now the beta function is basically the multiplying factor of the transistor. So a transistor can act as an amplifier, or really like a magnifier. So the current on the base times by the beta function is equal to the current coming from the collector. So let's have a look at this. Well, an example here, a wall-biased NPN transistor with a beta value of 125, so that means it has a magnifying factor of 125, has a current of 2 milliamps on the base. What current will flow through the collector? Well, firstly we need to convert milliamps to amps, so 2 divided by 1000, and then timesing by our magnification factor, we get 0.25 amps. Once you have biased your transistor, so there's a voltage on the base, you can then apply an alternating current to the base as well, and that alternating current will be amplified through the transistor. But something that's important is with biasing, you don't want to bias your transistor too high or too low. Otherwise what will happen is you'll end up with something called clipping. And clipping is where either the transistor bottoms out and will not provide any current at all, or it reaches the maximum amount of current it can produce, even though you want to magnify the value further. And then at this point you end up with distortion and intermodulation occurring, which can cause something called splatter. So if you're designing your own amplifiers, which we're going to look at next, it's something that you have to do carefully, is just choose what value what voltage you're going to apply on the base of the transistor to avoid this effect, because otherwise it causes distortion and even possibly cause out of frequency or out of band transmission. Before transistors were really around, thermiomic valves were being used, and valves are still available even today. They should be used with caution because they they need a high voltage DC supply, which can cause quite a nasty shock, and is something to be wary of. But they work in a very similar way to a transistor in a way, except rather than being controlled by current, they're controlled by voltage. Essentially you have a glass vacuum with a cathode that is heated, and the electrons can effectively boil off is the term used from the cathode if a potential difference, a positive potential difference, is placed on the control grid, and then those electrons pass through the control grid to an anode, providing an electrical current. So you can have a small voltage on the control grid, and that can produce a very large current through the cathode. And it works very, very similar to a transistor. Okay, well, next up is how can the transistor be used to amplify? And you need to be aware of 3 different classes of amplification, but you don't need to really worry about the circuit diagrams. They're just there just to explain what's going on. So a Class A amplifier is the simplest form of power amplifier, and it uses just one single transistor. Effectively, the transistor is always biased on, so there's always some current flowing through the transistor. There's a capacitor that basically is placed on the base that will allow an alternating current to be placed on the base along with a biasing DC current, which is effectively keeping the transistor turned on. And that AC waveform will be amplified through the transistor. Now, the efficiency of a Class A amplifier is very, very low. They're less than about 30% efficient, which is not very good. But they are very linear. That means that they can be used for all modes of radio transmission. The next class of amplifier that you need to be aware of is called the Class AB amplifier. Now, Class AB amplifiers use 2 or more transistors biased in such a way that each transistor only conducts during half of the cycle of the input waveform. You have basically something called a push-pull amplifier. Basically, you have 2 complementary or matched transistors. They're matched because they have the same beta function. You might have one NPN type and one other PNP type. So one transistor will amplify for one half of the 180 degree input, and the other 180 degree waveform cycle, the other transistor will amplify. The transistors are set just so they are almost conducting electricity. So you have to bias them very cleverly and carefully, but once they have been biased, so they're just about to switch on, then the efficiency of this AB amplifier, or Class AB amplifier, is around 60%. And they can be used for all modes of radio transmission, so AM, FM, SSB, and CW, and digital modes as well. And in fact, they're probably the most common kind of amplifier that you will find in modern day transceivers. The final type of amplifier you need to be aware of is called the Class C amplifier. Now, the Class C amplifier is designed to have the most efficiency, but has very poor linearity. It's basically, you have a transistor that is not really even switched on, and will only really turn on for less than half of the input cycle. But this is fine for FM or CW, because FM does not require any information to be transmitted about the amplitude of the wave. Only the frequency of the wave is important, and that's the same with CW as well. We're only interested in the frequency of the wave, and the amplitude of the waveform is not important to us. They are actually common in most handheld radios that use FM. Okay, so a Class C amplifier, you want a handheld radio to be energy efficient because you're taking it out on the field, probably using a battery. So it's going to be around 80% efficiency, but they have the poorest linearity. So just in summary, Class A amplifiers are inefficient, but are very linear. They'll accept all modes of transmission. Class AB are fairly efficient with 60%. They will accept all modes, but they need a bit of setting up or biasing, although modern day amplifiers will be correctly biased at the factory. And then Class C amplifiers are very efficient, but are only good for FM or CW. Okay, final review of the section is the oscillator. Well, an oscillator basically is an electronic piece of equipment that produces a single sine wave, and it uses the process of feedback okay, going through an amplifier to maintain this oscillating signal. Just the same way as you might get feedback if you go to a concert or at a talk or conference, and the PA system will feedback, whereas you've got a frequency that's going round and round and round, constantly being amplified. Okay. Now, really, you don't need to worry about the circuit diagrams at all. You just need to know the names of the three common oscillators. But we'll talk a little bit about the three. The first one is called the Colpitts oscillator, and invented by Edwin Colpitts in 1918. Basically, you've got two capacitors and one inductor as the tank circuit, and it works from 20 kilohertz to around 2 megahertz, and it's got very good frequency stability. The next is the Hartley oscillator, and really the only difference in the design is that the frequency is produced by the tank circuit that actually has two inductors and one capacitor, which is just the reverse of the Colpitts oscillator. And if you look at the output, you can actually see from the 1K resistor there's a feedback loop going around, feeding the transistor here that's working as the amplifier. And finally, the last one that you need to be aware of is the Clap oscillator. You can see that the transistor has been set up in a Class A configuration, and slightly more unusually is that the tank circuit has three capacitors and one inductor, but there's still the process of feedback going back round into the transistor and around, and it's improves basically the frequency stability, and it can be varied to change the oscillator's frequency. If you want to have a very stable oscillator, you could use a crystal. So a crystal has a very, very high Q factor, maybe of up to almost 2 or 3 million. One downside of using a crystal is that they have very limited tuning, but that can also be an advantage as well. Something that's very, very important is when you create an oscillator, after you've made your oscillator circuit, you should consider having a buffer circuit as well. Now, the buffer circuit comes after the output of the oscillator. If you don't have the buffer there, what can happen is when you start pulling the signal from the oscillator, you can actually start to detune the oscillator. So you'll actually end up changing the frequency of the oscillator. So you end up with a chirping, or if you're transmitting Morse code, you end up with a slight chirping kind of sound. So in order to avoid that, you can have a buffer. So the buffer will amplify the output of the oscillator, and has will provide much more current than the oscillator could if required. Okay, that was a review. I hope that's been useful.